So now let's go to the third method to solve the problem, because in this case they do not ask you to use Stokes theorem. So of course, given the problem that you have, you can choose to invoke the Stokes theorem, but you can also try to evaluate the question, that is the integral of this curl of the vector v dot n in a more direct manner without using the Stokes theorem, right? So here, if you do not want to invoke the Stokes theorems, then uh, you have to evaluate the term one by one. Basically, the curl of the vector v, you have found what is this, but then now you have to find what is the unit vector n normal to the surface. So then when you don't use the Stokes theorem, so now your surface is basically the whole hemisphere. So the whole hemisphere, the surface is given by this equation, right? And now you will have to find a normal vector over this whole surface. So in order to do that, we have to recall to mind what we did for a 2D case. So for a 2D case, assuming that you have a circle, right? So you will have a line tangent to the point. For a given point, you have a line tangent to it, and then you can also define a line which is normal to the surface. And if you remember from the lecture on the gradient of a function or scalar potential, you will remember that this vector on this direction normal to the surface is given by del phi, right? So then now what you want to do is you want to find n. Basically, you have to take the gradient of the scalar potential or function and you divide it by the length of it, and you will get n. So in this case, my surface is given by this expression over here, and the gradient of it is going to be, so now the gradient of it is going to be I d over dx plus j partial derivative respects to y plus k partial derivative respects to z, and this is going to be x squared plus y squared plus z squared. And here you will have I 2x, right, plus j 2y plus k 2z, and this is equals to 2, and here is xi plus yj plus zk. And then you want to find what is the length or the length of this vector. So you will just have to take phi dot del phi, and this is going to be 2 times 2, 4, and you have x squared plus y squared z squared, and this is going to be because we have this equation, this is going to be equals to a squared. And basically from here, what we want is n is going to be equals to gradient of phi divided by gradient of phi. And this is here. This is 2 xi plus yj plus zk divided by 4a, and then you can cancel this so that this is 1 and 2, so this is half of xi yj plus zk divided by a. Okay, so then now we have the n for this term. So now we will evaluate the whole expression. So now we will put it into this term. So if you remember what we did just now in the first slide, that was to look at this expression, and we will find that this curl of the v in this case is equals to negative 3k, and you want to take a dot product with respect to the n that we found just now was 1 over 2a, and this is xi plus yj plus zk, and this is the sigma. So here you just have to look at the k component, the k here. So here you have 1 over 2a, you can remove it, and this is going to be negative 3. So k dot k, here you have integral of sec d sigma. Okay. So now you want to evaluate this this term. So here you have to use the spherical coordinates, so that your z is now equals to r cos theta. So now theta, this is a polar angle. So, and then now you have to find what is this sigma. And here, if you remember, when you change from dx, dy, dz from the Cartesian coordinate to the spherical coordinates, where you have dr, d phi, and d theta. So here you have an additional term, which is r squared sine theta, where this theta is basically the same. This is with the z here, and this is the polar angle. So here we do not have a dr because your radius is constant. So here you can write d sigma as r squared sine theta d phi d theta. So here you are going to put it into this equation here, so that now you will have minus 3 over 2a integration of r cos theta, and this sigma, as we mentioned, is r squared sine theta d phi d theta. Okay, so now let's simplify it a little bit, and we remove r because there is no dependence on r for the integral part, and here you are going to have minus 3r over 2a, so r is going to be to the power of 3, and here you have sine theta cos theta d phi d theta. So now you have integration over phi and theta. So there is no dependence on phi here, so it's easier to solve it first. And phi is your azimuth angle, so on your xy plane you are going to go from a 0 to 2 pi, right? So here you will have minus 3r to the power of 3 2a, and here you have 2 pi for the phi, for the integration over the azimuth angle. And here you have sine theta cos theta d theta. And here you can notice that cos theta d theta is basically the differentiation of sine theta. Okay, so if you write u equals to sine theta, you will have du equals to cos theta d theta. So if you integrate du, basically you are going to integrate cos theta d theta, and this is going to be equals to sine theta. So here, when you integrate this, you will see that cos theta d theta is over here. You can replace them, and this whole thing is now equals to minus 3 r to the power of 3 over 2a and 2 pi, and then here this is going to be sine theta. So sine theta, you go from 0 up to 2 pi. Okay, because you are looking at the hemisphere like this, so you have your z. So you go from 0 and up to 2 pi. So here you have 0 to 2 pi. So I just need more space over here. I will remove this part. So here's sine, sorry, not 2 pi. This is pi over 2. Sine pi over 2. So now I have sine pi over 2. This is 1. Sine 0 is 0. So I have 1 over here. So here I will have minus 3 r to the power of 3 over 2a and multiply with 2 pi times 1. Because sine pi over 2 is equals to 1. So now if I cancel this and this, so now r, if you remember from our equation, my r is equals to a. So I can replace minus 3r with a to the power of 3a pi and a, and this will cancel, so I have minus 3a squared pi. So here, this is the answer for the method 3, where you integrate this expression as it is, but your n is different. So now here, if you notice, there is 3 ways to do. Yes, one is as we have done, you integrate over the surface of the hemisphere, but here your normal vectors is perpendicular to the surface. So as you move along, then your normal vector is going to change in directions. So this is the third method. The second method that we have done was to integrate over this circle on the xy plane, because this circle bounds the surface. Okay, so in the Stokes theorem, it is used for any kind of surface. It means it doesn't care what kind of surface that you have over here, but it is supposed going to be the same if you evaluate just along the line that binds the surface. Okay, so that is on the right hand side of the Stokes theorem. On the left hand side of the Stokes theorem here, what you have done is basically you try to find the surface over here. So this is the surface, and you are going to look at where is the vector normal to the surface. So in this case, this is my surface, and the vector normal to the surface is along the z directions. Right. So that is what we have done for the method 1. So I hope you have managed to appreciate some of the application of the Stokes theorem, because as you have seen, the Stokes theorems simplify the calculations a lot. So if you have any problems that you want to ask, please feel free to post a message to me. So as a wrap up, I picked 2 exercises over here. Let me just show you. So I picked two questions, number 6 and number 7. So please try this on your own, and we will discuss the solution in our next class. So all the best.